Hello, my name is Michael Sinenko, and I am going to be describing the heat diffusion equation, why it is important for our understanding of heat transfer between or inside or outside, going into an object, going out of an object. I'm going to be getting into how it goes into that object, how it leaves. I'm going to show you a control volume, a differential control volume, how that heat gets transferred into that control volume. And we're going to start especially off with a just any kind of arbitrary object, and it can have any kind of shape. It doesn't matter. Let's just say it's like some kind of strange object, can look anything, have any kind of shape. And the thing about this object is it can be made out of anything, but it's also going to have a constant K that we are going to see in some of the equations here in the future, as I describe. And this is going to be the heat conductivity constant. Let me go ahead and write that, heat conductivity. And this property of a matter is an intensive property. It doesn't change, generally speaking, at least. But this is going to help us with doing our equations, going into, how that heat is being transferred within this object. But what we can do is, instead of just looking at this object completely, for what it is or whatever it could be made out of, we could just say that there is a small little differential control volume in here, and it's going to have three spatial dimensions. Let's just say it's going to be the temperature, function of x, y, and z. We are looking at this in Cartesian coordinates. Now, if I was to actually make this a lot larger so we can actually see it, could be a three-dimensional object here, and how heat flux is moving through this object. There is a heat flux that goes into perpendicular to each plane and leaves perpendicular out on the other side. If we were to define our Cartesian axis like this, we could say that this way, z going straight up is going to be the z direction, and then y is going to be along, and just say this is a y. You can say that this way would be z, or actually let's say, okay, well, we could just say that's y and that's z, and then we could call this x. It doesn't matter as long as you're consistent, honestly. As long as you're consistent, it works. So the thing is about these differential control volumes is it's going to understand how heat is being transferred on an infinitesimal level. If you understand how the heat is being changed on an infinitesimal level, it's going to be less guesswork. You're not going to look at averages or anything. You're going to understand exactly how heat is coming into one object in three-dimensional space and leaving out in that three-dimensional space, of course also in reference to time. Now, what we know is, let's just say that within this small differential volume, there is a heat, Qx, a heat flux, that is going this direction. We also see that there is a heat flux, y, going that direction as well within this differential volume. And there is also one going this way, Qz. Now, one thing I didn't really say, since this is a differential volume, we can just say that this is going to be dx. This right here going up is going to be dz. Maybe I shouldn't write, yeah, the dx is right there. And then we can have a dy. So what is our volume going to be? Well, length times width times height, or depth, however you want to say height, or whichever dimension it is, dx, dy, and dz. Okay, well, we know that there is heat going into it. There's a heat flux going into this object, this differential object. Well, obviously, once we have heat in, what else are we going to look on? We're going to look at what is going out. And this is going to be Qx, in this case, in the x direction, plus some infinitesimal change in that direction as well. So whatever it's going to be defined on at that distance, because this is absolutely arbitrary, We're just gonna call that dx, whatever that distance is. And it's gonna be the same thing when we are looking at the y. It's gonna be the heat flux y plus dy, and the same thing for our z term here, qz plus dz. We're also within this object, or differential volume, should I say, beyond or within its planes. There's also going to be a term here, which I'm going to guess, well, I'll just like draw a line down here. This can be the energy generated within the system, and also the energy stored within a system, and the rates, of course. And they're going to be very important when I'm going to be relating this heat diffusion equation and how the heat is being transferred across this these planes or this differential volume with the conservation of energy equation. Now let me extrapolate a little bit more on some of these terms. Okay, so first of all, the qx plus dx. What does that actually mean? We can actually set that equal to the heat flux at that given point, that Cartesian point, whatever it is, plus the differential change in that direction times some arbitrary distance x, infinitesimal change in x. And this is also going to be the same for, y. We can have this for y, of course. Let me just write those real quick, just so they are here, and so you guys can see them. That's y. Y. And let's do the same thing for our z term. Z. All right, qz plus z l z times the change in differential distance z. Okay, so we basically defined what's going in, we defined what's going out, we extrapolated on what that actually means. Is the gradient of heat transfer that's going through, with the infinitesimal multiplied times the infinitesimal change in that direction. Now, EG here, with E subscript G, is the energy generation. What is the energy generation in our case here? Well, it's going to be Q dot. And this is the amount of heat that is generated within our object, and it's going to be measured in watts per meter cubed. But we also need to multiply this by our differential volume. Now, this is basically going to be, if you understand it in theoretical terms, of it's the heat that is generated and the thermal energy that is generated when it's being transferred from a different type of energy, whatever kind of energy that you could think of. It could be like an electrical energy, it could be like nuclear physics, who knows, this could be like a part of the sun or something, or it could be, I think I just said chemical energy. It could be any kind of energy that's being turned into this heat energy, and that's what that is going to be defined as. And that Q was the energy rate heat generation term, essentially, that Q dot. And that's our differential volume, as we were just speaking. And then going to the EST, it's the rate of the energy storage within our control volume here. Now, how do we actually define that? Because it's just one term. Okay, well, it's going to be our density, the density of whatever this kind of object is for our control volume, whatever kind of substance it could be, lead, metal of some sort, you never know, times our specific heat capacity for that object, times also the differential temperature in respect to time times dx, dy, and dz, if you guys can see that there. So that is what that is going to be. This is the time rate change according to the density, multiply this by specific heat capacity, and that's how we are going to define that. Okay, let's see, what else do we have here? Okay, looks like we have everything that we need for the next part. Okay, well, the conservation of energy, we can define that now. So we have all the terms that we need now. So, okay, so we know that there is something going in, there's something that's being generated, and then there's something leaving, and then that's going to be equal to what's stored. Clearly, because you have something going in, some of it gets stored, some of it leaves, just depends. So you would have, in this case, let's just say the rate in, you can just follow me here for a second. Got my eraser here, that's the way I have it. E in, energy in. What's the generation? What is out? And then what is going to be stored. Okay, so this is the conservation of energy here. Conservation of energy. And what can we do with this? How is this going to help us, you may ask? Well, especially in our case with our differential volume, how is heat transfer going to work? Well, we can put these different rates in, and then we can define how this energy is changing within our control volume. How is heat being put in, how it's getting taken out. And of course, since this is an infinitesimal volume here, we can basically then all of these would be added up, or they would be compared to one another, because heat is actually, it would be a gradient in real life if you were to look at real life situations. So what is going in? Well, we already said there's a heat flux going in every spatial direction for us. Well, we have a Qx, so we can just say there's a Qx, there's a Qy, there's a Qz. And by the way, this is plus, I caught that. This is plus, everybody. And then you have the amount that's being generated here. So what did we say? This is the energy being generated times the differential volume here, which was in watts per meter cubed. So we have our Q dot here, dx from dy and dz. All right, and now we also know that there is some energy that is going to be going out of our system, and that is going to be what we said was the, in our case, our heat flux at the certain location plus the differential change in the heat flux in respect to the direction times the change in the direction infinitesimally in that direction. Mouthful, I know, but that's the best way I guess I can explain it. So then you would have that out here, and this is of course is going to be subtracted out. So we can just put this as the qx plus dx minus qy plus dy minus qz plus dz, and all of that, since I'm running out of room, is going to be equal to what we were saying here. This same thing, our density, our specific heat capacity times the differential change in temperature respect to time times our differential volume here. Okay, so now we have this equation. Is there a way we could actually simplify this any further? And the answer to that question is absolutely yes. But there's something that we haven't talked about very much yet, or I haven't mentioned very much yet, and that was Fourier's law. So Fourier's law, Fourier's law, oh, whatever, the audience understands. Fourier's law, well, we could just take any arbitrary distance in heat flux in any arbitrary distance. It doesn't have to be x, y, or z, just whatever, but I'm just going to use x. That's going to be equal to the negative of our heat conductivity multiplied by the differential area going in that direction. So if I was to look at this is Qx. So this is the area. And what is that governed by? The area here is the y, and it's the z, right? So you would have these little, like, if you want to say like windows, if I was to look at this going this way, it would just look like this, like if your eye is looking this direction. Well, it would be going this way, and you would take the sum of all of them in that direction by multiplying by how many of them there are in this direction, which is going to be x. So if this is going to be our, in this case, like let's say this is our z going up, this is our y, we would have that. So what do we do here? Obviously we would multiply by the differential amount in y and differential amount in z, and that is going to be multiplied by, looks like, in that direction. There you go. And let me remove this here for a second. This would actually be the same for every other direction as well. So you would have qy is equal to this, but you would just change it. If it's y, then this would be dx dz, and then it would be in the y direction here, and then in here you would have this again, but since it's the z direction, you would just do x and y, and just keep those two the same. So we have everything we need so far. Now, going back to this equation right here, we need to simplify this. What do we do with this? How do we cancel some terms? How do we get everything to come together into one nice, neat differential equation? Well, what we could do is we could see that this, and this is literally only the negative of all of these. Look, this is just positive here. I didn't write the positive, but you could see that. So all you would have to do is take each of these and multiply them by -1. It's not the exponent, so I want to say that it's multiplied by -1. Well, what would you get here for at least the x component? You have negative, and then you would have a negative here, and then minus, and then you would take this term, all of this. Why don't I change the color real quick? I got red. Let's just so we can see. You take all of this, let's call this box A, and you would put A into here. And you would do the same thing here. You would multiply this by -1 and multiply this by -1, the whole entire equation. And then you would have this being a, okay, we said this was A, this would be B and C. And you would put B and C here. And then what you're gonna realize without me writing everything out is if you see this negative QX, this negative QX is gonna be replacing here, and it's gonna be minus this right here, this change in the heat in the respect to the x direction times dx. That's going to be only minus it, so it's not going to be part of the whole entire equation. They're not being multiplied together. So what you're going to notice is that this x right here will be will cancel out with this one, because it will be qx minus or qx positive minus qx. And the same thing will end up happening for all the other terms. This one will disappear, that one will disappear. It will keep this for a little bit, and then we'll keep all of this for a little bit. But what we're gonna end up with is this. You would just have the negative of all of these. You have this over dx minus y and then, of course, you would add this back in, the generation term for our energy generation within our control volume infinitesimal one. And then, of course, you would have this still equal to that energy storage term. dx, dy, dz. Okay, well, there's actually some more things that we could do. And it's good that I actually defined this Fourier's laws before going in there, because now, how I said A, B, C, we can do the same thing with all of these, but we don't have to multiply by -1. So what is interesting about this is this can go in here, and then this can go in here. Oh, look at my drawing there, buddy. So in here, and then this one can go in there. And what you're gonna, I'm only gonna do this for the one because I don't wanna turn this into a gigantic equation that's like this long. It's for just one term because it follows the same for the rest of the terms. So you would end up having your partial derivative here. And then this qx term just be a -k dy dz, and then del t del x. And all of this multiplied by dx, all of this divided by del x. Well, we can simplify this a little bit more. First of all, what you notice is these two negatives will cancel, so that'll go away. So let me just say that this is the same thing as del x going to be k times our, let's see, or let's just do dx. I'm gonna rearrange these terms, but the dx is right there. dx, dy, dz, and then we're gonna have del t, del x. And the thing is that what you're gonna realize about all of these, if I do this same exact method for every single one of these, it's still gonna end up being d, in this case it would be dx dz, but then the y term would come in because it's being multiplied by dy, and the same thing would end up happening in the, I forgot a dz here, by the way, or there is a dz term here. But what is going to end up happening is you're going to have this control volume type equation come back in for every single term. But then what you're going to be able to do is factor it out in front, because it's going to have that in common with every single term. And then the beauty of it is that once you factor this out, it'll be out here, dx, dy, dz, and then you'll have all these different partial derivatives. It'll be like d del x, and you'll have, it'll be k, and then in our case del t del x, and then it would do the same thing for the y term and everything else. So dot 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 for y, every same thing, but for y and for z. But on this side of the equation, what's going to end up happening is this is going to go away with this. So if I wanted to, here, I'm going to write this up here, the final equation. It would end up being del x, k, del t, del x, and then this plus in the y direction, k, del t, del y, and then plus del z, thermal, or heat conductivity, and this, and all of this would be equal to our rho, specific heat capacity, PT, in respect to time. And that, ladies and gentlemen, is our equation that we were looking for. And thank you for watching.